Okay, so the derivative function. What is the derivative function? Well, in the first chapter, we pretty much spent a lot of time trying to figure out what is the slope of a tangent at some point on a graph, or what we would call the instantaneous rate of change. We used it so much, we had an equation for it, right? This one here. And we called it the difference quotient, or the limit of the difference quotient. Since we use this so much, we're going to give it a special name. We're going to call it the derivative function. So you've already been doing derivatives. I just haven't told you that yet. Right? And there's lots of different notations that people use in calculus to represent the derivative function. Notice the one I used here. I wrote f prime, which looks like a little apostrophe, but I call it prime, f prime at x. That's called the Lagrangian notation. The Newtonian notation, you would write y and put a little dot above it. And the Leibniz notation, since this is sort of a change in y over a change in x, but instead of writing delta y over delta x, it's a very tiny change. And so we represent that with dy by dx. So 3 different notations to represent the same thing, the derivative function. So let's look at these 3 graphs down here. These 3 graphs are cases where the derivative won't exist. Really, you're just looking at, for example, this middle one, where you end up with a vertical tangent. Because the derivative is finding the slope of a tangent. And if the tangent is vertical, well, that doesn't exist. Okay, it's undefined. And that could happen in, say, a case like this. It could happen if you have a discontinuity. The derivative won't exist there. And it could also happen at sort of a cusp, right, where the slope changes from this to this. Right at the cusp, as it changes from this to this, it'll be vertical. So these are 3 cases where your derivative won't exist. All right, now what we're going to do, I'm just going to do a little example down here. We're going to find the derivative for x squared. But I'm not going to tell you to find it for x squared at a certain point, like x equals 8 or x equals 2. Right? Instead, we're going to find it for some arbitrary unknown value, x. And then we'll be able to define what that derivative function is for x squared. So we're going to use the difference quotient, just like we did before. Right? The limit of h equals 0 of f at x plus a little bit of h minus f of x all over h. So when I do this, I will get the limit as h approaches 0 of, so x plus h squared. Essentially, I'm just subbing x plus h in for x. So I have to square it. Minus f at x, which is x squared, all over h. All right, so let's expand that x plus h squared as, h approaches 0, not x. And so we're going to get x squared plus 2hx plus h squared minus x squared. All right, so here we have x squared minus x squared. So that's going to cancel. And that's all over h. Okay, so I can factor out an h. So the limit as h approaches 0, factor out an h, and we'll get 2x plus h all over h. So h cancels. And then as h approaches 0, this term goes away, and we're just left with 2x. So if f at x equals x squared, f prime at x, or the derivative of f at x, equals 2x. So now we can determine the slope of the tangents to x squared at any point we want. We don't have to keep doing the limit because we know what the derivative function is. It's 2x. Right? And if you look at this graph here, right, here you have this blue point here, that's x squared. Okay. Now if we were to find the slope of the tangent at x equals 1, so that's an option, we'd do f prime at 1 equals 2 times 1, because it's 2x, equals 2. Right? So the slope of this line here is 2. If we were to do it for this point here at 4, you just do f prime at 4 equals 2. Oh, sorry, that's not at 4. That's at negative 2. Take the x value. 2 times negative 2, and we get negative 4. So the slope of this tangent would be negative 4. Right? And if you were to just graph the derivative function, it's just a linear function that looks like this. So we can see if you're doing f at negative 2, negative 2 would be all the way down here. It doesn't fit on the graph, but you would see it would be negative 4. Right? If you were to do f at 1, right, that equals 2. Right? So if you have a quadratic function, the derivative ends up being a linear function. So you go from degree 2 to degree 1. Alright, so let's go over some other functions. Here it says to determine the derivative f prime of t from first principles. From first principles means to use limits to figure it out. Now you're probably asking, wait, is there another way to figure it out? Yes, that'll be tomorrow's lesson. For now, we're going to do it from first principles, because we're just being introduced to this concept. And it's the same thing we've done before. It's just, like I said, instead of finding it for a certain point, we do it for an arbitrary point, an unknown value. So I'm going to do this one over here. So we have f of t equals the square root of t. Okay. Well, if we're going to find the derivative function f prime of t, that just equals, again, the limit of our difference quotient of the square root of t plus a little bit of h minus just that function at t all over h. Alright, it's a bit messy, but we're going to multiply that by its conjugate. Okay, I'm going to rationalize the numerator. So we have the square root of t plus h, and instead of minus, we're going to switch that to plus square root of t divided by the exact same thing. That way we only multiply by 1. Right, so our numerators is a nice difference of squares. So it'll reduce to t plus h minus t. So that's great. The t's are going to cancel. And on the denominator, I am not going to do anything with that. I'm just going to leave it as is. Plus h plus square root of t. Alright, so t's cancel. And we're left with h over h. So those are actually going to cancel as well. But I'll write it out. H over h times t plus h, the square root, plus square root of t. So yeah, h is going to cancel. And then as we sub h into 0 now, which we can do, right, we'll get 0 here. So we get 1 over the square root of t plus the square root of t, which is just 2 times the square root of t. So our derivative function, f prime at t, is just 1 over 2 times the square root of t. Alright, so the next example says determine the equation of the tangent to the graph. So it doesn't want to find the slope. It's not asking you to find the derivative function. Just says find the equation of the tangent to this function at this point. So in order to figure out an equation of a tangent, which is a line, we need to know the slope. And we need to know some point on that line. Well, we can figure out a point, right? Because it's telling us x is 2. So if x is 2, we can figure out what the value of that function is at 2. And you get, just substitute 2, so you get 1 over 2. So there, we have a point, 2.5. So now we need to find the slope. Now to find the slope, we're going to first find the derivative function. And then if we set x equals 2 into the derivative function, we will know the slope of the function, or the slope of that tangent at that point on the function. And then we can go ahead and figure out the equation of the line. So let's start with finding the derivative function. So f prime at x. Alright, well that's just going to be, first we're going to substitute x plus h. So we get 1 over x plus h. And then just minus that function at x, all over h. Alright, so in this case, I'm going to add or subtract fractions. So I want a common denominator. The common denominator I'm going to pick is just the multiple of these. So it's going to be x times x plus h. Alright, so if I do that, so I multiply this one by our common denominator. 1 cancels and I'm just left with x all over this common denominator. Subtract by this one would be x plus h all over the same common denominator. Now that they're both over the same common denominator, I can just put that common denominator in the denominator. And I like saying denominator, apparently. So we still have that h here, but then we also have this x, and we also have this x plus h. So let me change colors and go through what I just did. I may have skipped a step. Let me simply take the numerator. I'm just going to work with the numerator here. So let's ignore this divided by h. And I have two fractions, 1 over x plus h minus 1 over x. So what I can do is I can multiply each one by the multiple of the two denominators. Right? It's no different if I had 1 over 3 plus 1 over 2. The common denominator there would be 6. Right? So I can change each fraction to one would be 2 over 6 and the other would be 3 over 6. Well, how did we get 6? Well, 6 is just 3 times 2. Alright, so I'm going to change that common denominator, in this case, to be the multiple of those denominators, which is x plus h and x. Alright then, well, where did this 2 come from? Well, all I did is multiply each one by those two multiples, so 3 times 2, but 3 sort of cancels out with 3. So I'm left with 2. Okay? And so, let me rewrite this in a different color. Imagine doing, not imagine, this is exactly what we're doing. We're multiplying each fraction top and bottom. 2 times 3. Okay. So this cancels with that, and you get 2 times 1, which is 2. And that's over the common denominator of 2 times 3, which is 6. So I haven't done anything, right? 2 over 3 divided by 2 over 3 is just multiplying something by 1. And I do the same thing to the other side, to the 1/2. And I'm doing this here, but instead of 3 and 2, I have x and x plus h. So I multiplied the numerator by both x and x plus h, but it's the x plus h term that cancels, and I'm left with just x. I do the same thing here. Multiply by x and x plus h, but it's the x term that cancels and I'm left with x plus h. And now I'm going to bring back this. So this is all over h. So I can simply take this denominator and put it with the h. So if I continue from here, here you're going to get x minus x. So those are going to cancel. And I'm left with minus h. So I have minus h. And, oh my goodness, never do what I just did. I forgot to write the limits. As h approaches 0, the limit. As h approaches 0, the limit. as h approaches 0. Okay. Oh, that was terrible of me. All right, divided by h times x plus h. So our h cancels, and we're left with the limit as h approaches 0 of -1 all over x times x plus h. But if h approaches 0, now I don't need to write the limit because I'm going to apply it. Right? You just get -1 over x squared. So there's our derivative function. F prime at x equals -1 over x squared. So if I want to figure out the slope of the tangent at 2, we're just going to figure out what that derivative function is at 2. So it's -1 over 2 squared, or -1 over 4. So now that I have the slope of the tangent at 2, and I have a point on that tangent, I can figure out the equation of that tangent. And how I'm going to do that is I'm just going to use the slope equation. I'll use a different color here. Slope equation, if you remember, is just m. That's a terrible m. Let me write that again. Okay, it's just m equals, well, y minus y naught over x minus x naught. Well, we know the slope is -1 over 4. We have an arbitrary point y minus a point on the line, y naught, which we know is 1/2. Because we know a point on the line, so -1/2 all over some arbitrary point x minus 2. So now I just have to rearrange and solve for y. So you're going to get y minus 1/2 equals -1/4 times x minus 2. Or y equals -1/4 x minus 2 plus 1/2. And if you want, you can leave it like that, or you can expand to slope-intercept form and write it as y equals -1/4 x, and then we get plus 2/4, which is plus 1/2, and we still have this plus 1/2. So y equals -1/4 x plus 1. Okay, so the last problem says determine an equation of the line that is perpendicular to the tangent of the graph at x equals 2. So we already figured out what that tangent is, because it's the same function, 1 over x, and so it's the same derivative function, -1 over x squared. But we want something that's perpendicular. So let me use a different color here. I'll use blue. So what you can do is you can remember that the slope of that line that's perpendicular is going to be the negative reciprocal of this slope here. So if this line has a slope of -1 over 4, the new line of the perpendicular one that we're looking for would be, well, take the reciprocal, so flip them, which is just 4 over 1, and take the opposite sign. So it's just 4. Okay. Now we still have the same point, right? Because the same point would be on both, which is 2 and 1/2. So all we need to do is apply the same slope formula. M equals y minus y naught over x minus x naught, but we're using this slope instead, the line that's perpendicular. So that'll equal y minus 1/2 over x minus 2, and you just rearrange, so you get y minus 1/2 equals 4 times x minus 2, or y equals 4x minus 8 plus 1/2. Well, I said x, but I didn't write it. So y equals 4x minus 15 over 2. So there's the equation of the line perpendicular to that tangent, but still intersects at that same point.